Okay, so these are the equations you're going to be responsible for the open channel flow experiment. Okay, so as I mentioned before, Froude number here, if you have a Froude number less than 1, it's subcritical. If you have a Froude number that is greater than or equal to 1, then it's supercritical. So your Froude number, v over square root of g times y. Velocity of v is the velocity in the section that you're testing. G is the gravitational constant, and y is the channel height. We have 3 sections here, so there'll be 3 velocities, 3 channel heights. Okay, so you'll be able to calculate 3 different Froude numbers for each case. Okay, and again, the only critical one, i.e. the one that is 1 or greater than 1, should be in the middle section here in section 2. Okay. All right, so how do you find velocity? So we can say here that your dynamic pressure is equal to 1/2 times rho v squared. Okay, dynamic pressure is also equal to your total pressure minus your static pressure. Okay, as you can see here, this is your channel depth. Your static height here, okay, is above the water line, and your total height here is also above the water line in its particular section. Same for all the other ones. Okay, so rho times g times ht minus rho times g times hs is, obviously the same thing as saying rho times g times the quantity ht minus hs. All right, so we set both of those equal to each other because dynamic pressure is this one and that one. All right, so we say 1/2 rho v squared equals rho times g times the quantity of ht minus hs. All right, so now we rearrange this to get velocity by itself. Okay, so you multiply each side by 1/2 times rho. In this case, both of the densities are the same for the water in the manometer and the water in the moving fluid. They're both water. Okay, so then we just take the square root of that. We end up getting velocity equals square root of 2 times g times ht minus hs. Okay. Now, with all this information, we are able to go and find your head loss. Okay, you'll have an experimentally determined head loss equation here, which is based on your Bernoulli continuity sort of stuff, and then your theoretical here, which includes your Froude number there. It only works, the theoretical equation, only works with a supercritical Froude number. So this will only work for the head loss between states 2 and 3 because there is indeed a hydraulic jump. With this equation, you could use it from between states 1 and 2 and 2 and 3. You just have to change your subscripts of 1s to 2s and your subscripts of 2s to 3s. So let's go over this. Here we have y1 plus v1 squared over 2g plus s sub 0 times l1 to 2 equals y2 plus v2 squared over 2g plus your head loss from 1 to 2. Okay? So your S sub 0 here, what is that? So effectively, we are going to be testing in this lab many slope values, so 5 different slope values. Okay? Now, the slope in this lab is going to be going downstream like that. So effectively, what you lose in potential energy in state 1, you will gain in kinetic energy from the downward slope in state 2. Now, there's going to be some head loss associated between the 2 states, so that head loss might indeed be greater than the potential energy gained as you go down slope, but that's what we're going to figure out. So either way, if you have a slope, which is a factor of rise over run, and you have a length component, you have effectively rise over run times run. Rise over run times run equals rise, okay? So for states 1 to 2, you will have a 36 inch length, and then from states 2 to 3, you'll have a 42-inch length. It'll be up to you to change all these units into kilograms, meters, and seconds. For the entire lab, in fact, you'll need to make sure that, whether or not you record it in millimeters, you make everything into kilograms, meters, and seconds. Okay? So yeah, there are some other theoretical equations for this. The Q at the sluice gate, so volumetric flow rate at the sluice gate, you are responsible for finding those yourself online. Okay? Other than that, that should be about all. What I'm going to do now is I'm going to zoom in on each section, which will allow you to read all the data points you'll need to use all these equations, okay? So for the data points, I want you, for each section at each slope, I want you to record the static height 3 times, the total height 3 times, and the channel height 3 times in each section, just so that you could average them and get a more accurate result. Now, the thing about these, which I'll explain before I turn the machine on, your total height is going to be the only manometer height out of the 2 that will have any significant height, okay? Now, your static height might look like it is slightly negative sometimes. It is not. It is almost always 0 or slightly positive, okay? To give you a flavor, when I was in lab, we were never required to get the static heights because they are more or less negligible, but conceptually it's important for you to know that whenever you're finding the velocity of a moving fluid, you need both static and total heights, okay? So I'll throw the machine on and I'll go over with you how to measure all of these variables.